Welcome to this session of Shadow the Scientist. MegaCam eyes wide open on the sky at the Canada, France, Hawaii telescope. My name is Jamika Marshall, and I am the Shadow the Scientist Programs Manager. I am very pleased to have finally been able to schedule this session for you and for the students here. Now, we are in for a special treat as we will be joining the Virja Katu, who is the resident scientist at the Canada France Hawaii Telescope. And we have remote observers with us, Jessica Nagasako, who is currently there controlling the telescope, as well as Jasmine Silva. They will be our science hosts for this session. Now, before I take it over to Viraja to give an introduction to Canada France Hawaii Telescope and to your experience that you'll have in this session, I'll go over to you, Nagaraj, to introduce us to you and your community of brilliant scholars there.
So, thank you, Jamika. And dear scholars, we have gathered here for a special session today. So this is an opportunity that we got through Jamika, as she mentioned. Uh, Thanks to her efforts and thanks to the dedicated efforts from our team also for setting up this call. So, Shadow the Scientist is a program which aims at giving this a holistic experience of a science experiment, how a science experiment happens, especially on the astronomical scale, on the astronomical background, to scholars. So, connecting like minded scholars, like minded peers, like minded science enthusiasts, and also scientists together on a single online platform where you can directly interact with peers, with the scientists, clear your doubts, and also where you can directly see the experiment that they are conducting. So this is a wonderful opportunity for all of us. I'm sure a few of you will be fascinated by the sky, by looking at the stars, by the astronomy. So this is an opportunity for you to ask any doubts, right? No question is a small question or no question is a big question. We all know that you are going to enter your 12th grade, so you can ask any questions related to career in astronomy or anything related to astronomy with the scientists and with our team here. So to just give a small context about the students here, we received around 100,000 applications for 3,000 slots last year. And these are few scholars, around 30 scholars from the region called Bangalore in southern part of India. It is called the Silicon Valley of India. So we have, as part of their scholarship program, we have a 4-day residential training for which they have come, and today is their last day. And we are super geared up and very happy and looking forward to this session. So these are meritorious scholars who have excelled in their 10th grades, who have gone through our selection process, and who are sitting here. So these are our proud Vidyadhan scholars, our proud Vidyadhan stars here, will be joining.
Congratulations to all of you students on all that you have achieved for all of your success. It is an honor and a pleasure to have you in this session with these amazing astronomers here. And so let me go ahead and switch over to our main science host, Virja Katu, to get some introductions going and to explain how she will take questions throughout the session. Welcome, Viraja.
Thank you so much, Jamika, and thank you, Nagaraj, for introducing to your wonderful group. I'm really excited because I am originally from India. I'm now a Canadian. I've been living in Canada for 14 years now, but I'm originally from Mumbai, India, and I have visited Bangalore, so I quite remember the place. So thank you so much, everyone, for joining. It's a pleasure to have you for today's session. I am a resident astronomer at the Canada France Hawaii Telescope. And as a resident astronomer, I have several duties to perform. I do my own research, so my expertise is actually studying supermassive black holes and the dense environments, how the gas moves around supermassive black holes in massive galaxies. But my time is also goes into supporting nighttime operations here at CFHT. So nighttime operations include how do we actually schedule observations for observing, and we'll talk a little bit more about that during the session as well. Supporting all the nighttime operations here at CFHT. And then a third part of my job is actually doing software programming slash instrumentation. It's basically includes handling the instrument. Is the instrument performing well? Is the data coming out of instrument fine? Doing some of the data processing for finally distributing the science data to the astronomers around the world. So these are different components of my job. I try to distribute my time pretty much equally in performing all of those duties. Other than that, I love doing outreach, and that's how I'm here hosting the session. So I love talking to people and doing a lot of science and astronomy outreach in general. So that's all the parts of my job here. But we don't only have astronomers at CFHT, we also have other people. So we have engineers, people of the instrumentation team working on the instrument. We have operations group. So these are the people who work on the telescope. There are people who work during the daytime. There are also people who work during the afternoon time, and this is pretty much to get the telescope all ready for observing during the night. And then during the nighttime, we have remote observers such as Jessica and Jasmine, who will introduce themselves in a short while. So we have remote observers who take care of actually collecting science data from our remote observing room where we are situated right now. And we'll also talk about that a little bit later. So we have a bunch of different people from different backgrounds, different expertise working all together just to make one single telescope operational all 365 days of the year without breaks. So with that, yes, and before I forget, so the session will cover how we do remote observing from a control room. And that includes, and by remote observing, I mean, we're not physically at the location where the telescope is. And I'll show that to you once we actually start talking about the session. So how we actually do remote observations, but feel free to ask any questions you have. As Nagaraj said, there are no silly questions, small questions, or big questions. Please ask your questions. If you wanna, you can relay your questions to Nagaraj, or if there is someone who wants to come and speak up on the video, they can please feel free to come up and ask your question. You can also put your questions in the chat. I'll keep monitoring the chat as we are talking, but we'll see how best it works. So I think with that, I'll pass it over to Jessica to introduce herself.
Hi, my name is Jessica Nagasako. I'm originally from Oahu. I went to the University of Rochester for the past 4 years, graduated May 2024, and now I'm here and I work as a remote observer. What else should I say? For context, I'm working right now, as Rita just said, so I'm kind of like back and forth. My mind's a little back and forth right now, but yeah. Happy to be here.
And since Jessica is actively observing, I'm another one of our remote observers, so I'm here if she's busy or to help answer any other questions.
Thank you so much.
Went to UH Hilo, grew up here, and was lucky enough to get interested in astronomy, just like Jessica. So we love our jobs and love outreach and are happy to be here.
Thank you so much, Jasmine. Jessica, Jamika, do you want to add something in?
No, Virja is all you. Start us off with where we are. I'm in Honolulu on Oahu right now, and I believe Jessica said that she's from Oahu, but now she's there on the Big Island. So set the stage for us. You're in the CFHT remote control room. Where is that located?
Sure, absolutely. So let me share my screen. Okay, so I've shared my screen just to confirm with Nagaraj. Are you able to see the Google Maps that I'm showing up?
Yes, yes, it is visible.
Okay, sounds good. So so this is from Google Maps, and geographically we are right over here. So these are the Hawaii Islands, right in the middle of the Pacific Ocean. If you zoom in a little bit more on that, you can see all the major islands, and we are here on the Big Island. So I'll keep zooming in a little bit more. And let me actually switch to the satellite image. So this is the Big Island. And we are right somewhere over here in Waimea. So Waimea is a town. It's not quite at the sea level. It's almost at 3,000 feet. But that's a town where we are located right now. That's where our headquarters is, and where we are sitting right now in the remote control room. Jasmine is in Hilo, and that is a town which is somewhere over here. So Hilo is the eastern part of the Big Island. And to point out where Jamaica is, I'll zoom out a little bit and we'll go all the way up here. So this is another island, Oahu, and Jamaica is on Oahu right now in Honolulu, which is the capital city of Oahu. Okay, so coming back to the Big Island, if I now switch to the terrain map, that actually allows us to see the elevation difference. And when I pointed out earlier, Waimea is right over here in the north, the town of Waimea, and all the way up over here, this is at an elevation of almost 14,000 feet. That's the peak of Maunakea. So Maunakea is it's a passive volcanic mountain. So there is no active volcano erupting on Maunakea, and that is where we have all the different observatories. The 11 Maunakea observatories now, which are on the top of the mountain. So that is at 14,000 feet, so quite high in elevation. This is a map that actually shows light pollution in different parts of the world. So we have, again, as I said earlier, we have the Hawaiian Islands right over here in the middle of Pacific, and which is well far away from all the pollution that we have on the mainland. So we are quite safe in terms of when it comes to observing for nighttime observing with telescopes. Now, if we zoom in on the Big Island, this is the light pollution map on the Big Island, and you can see there is a lot of pollution on the east and the west side, but not as much or almost negligible when it's somewhere over here in the middle of the island. That is where we have the Maunakea Peak, where we have all the telescopes. So not a lot of pollution over here, which means that we are very safe in terms of observing. Another thing I would like to highlight is Maunakea is actually a shield volcano. And what it means by a shield volcano is the airflow on top of the mountain is very laminar. So there are not turbulent motions of gas. A laminar flow is a very smooth flow of air without any turbulence. Turbulence is when you will have the hot and cool air churning up and down, and that is when a lot of turbulence, a lot of twinkling that you see with the stars, that is where it comes from, the turbulence at the atmosphere. When we are up so much up in elevation. We are already a lot higher in the atmosphere. We're clearing up a lot of the hot air downside, and so all the above is it's low oxygen level, but it's such a smooth flow of air that it creates a lot less turbulence for our observations than otherwise. And this is another image of Maunakea. This is ice cap Maunakea, and this is a picture from the Hilo Bay. So Hilo has a very nice shoreline, and this is a picture of the mountain taken from the shoreline. So just another amazing image to look at. These are all the different observatories up at the summit. All the ones that you see over here, all of these have domes. There is one that you cannot really see. It's an array of different dishes, which is not very visible over here, but this is how a dish looks like. This is a single dish antenna. It's the very large baseline array, which is not at this location right over here. It's a little bit on the downside from the peak. But these are all the observatories, and this is CFHT right over here. So CFHT is it's a 3.6 meter diameter telescope. So 3.6 meter is the diameter of the primary mirror of the telescope. You can see this as the shutter, the dome shutter is open over here in the image. These are all the different vents that you can see around the dome. And if you observe the background, then all the clouds are quite settled. Not very settled, I would say, but they're still quite settled down. So all the clouds are down. We are on top of the clouds. What that means is we can clearly see up in the space when we have a very good photometric night. And I should say, fingers crossed, we have a really good night tonight. It looks very clear, so we hope for very nice data coming in. So that's CFHT. And coming to what actually science can we do at CFHT. So CFHT has a bunch of different instruments. So the science you can do with the telescope depends upon, one, the weather. So we talked a lot about the conditions on Mauna Kea, but the second part is all the instruments that we have. So we have 5 different instruments here at CFHT. There are 2 imagers, so 2 imaging instruments. They're basically a camera. You're basically pointing a camera on the sky, taking the images. So that those are like just images of the night sky. So 2 imagers, one in the optical, so the visible range of the electromagnetic spectrum, one in the near infrared. So that's lower wavelength than the visible region. And then we have 2 spectropolarimeters. So spectropolarimeters are instruments that can record spectra of what we are looking at. So the spectro stands part of the name stands for getting spectra, but the polarimeter part of it is actually getting polarimetric measurements. So this is actually measuring how the polarization state of the light. And that is useful when we are trying to get magnetic fields around stars and planets. So, 2 spectropolarimeters, again, one in the visible, the other one in the near infrared. And then we have a then we have an integral field spectrograph. And that's basically another instrument that can do both imaging and spectroscopy together. So that's the one that we can actually use for simultaneous image and spectra collection. So a lot of science depends upon all of these different instruments, but the instrument that we have right now on the telescope is MegaCam. So MegaCam is our optical imager. So we are able to look at the full range of the spectrum in the optical, but also a little bit in the infrared. And MegaCam is a very wide field instrument. What it means by a wide field instrument is it can look at a very big patch of the sky at a single time and take images. And I'll show some of the very cool images with MegaCam and the kind of science we can do with this big instrument. So if you can see my screen here, this is actually an image taken with the MegaCam instrument on CFHT. Every speck of light that you see over here is actually a galaxy. There are some very, very bright blue dots, and not really dots, but these are, you may not be able to see my cursor very clearly, but so these are some of the white blue circle, very bright blue circles. And these are actually the stars that are in the foreground when this image was taken. So imagine when you're taking an image of the sky, you're actually taking a very big image, like a big backdrop, but then there are some, if there is something in the way while taking the image, these are all of those bright foreground stars. But all of the big things, the big blobs that you see over here, such as this one over here, some of the objects that you see here, some of the elongated objects, all of those are galaxies. And this is an image taken in a very special mode. It's called the low surface brightness mode. What that means is when you're taking an image with very long exposures, you're able to actually see the fainter objects in the image. In that part of the sky. So this kind of mode on MegaCam instrument is useful when you want to look at fainter stuff. All of the hue that you see over here in the background is all from the gas that's in this patch of the sky. But we are all able to see this hue of different colors, and that's all because you're trying to get the fainter stuff in the image that gives you a good contrast between the different elements of the image. So this is one cool picture. It's actually imaging something which is right over here at the bottom. And that is called Stephan's Quintet. So this is the image that it was actually, this is the interacting group of galaxies it was actually trying to capture. So these are different galaxies. They are gravitationally interacting with each other. All the fuzziness that you see in the image is all because of the gas in the galaxies as it is interacting with each other as they keep hitting each other at different iterations. So this is called Stephan's Quintet. It's a very famous interacting galaxy group that's studied a lot. And something like this, imaging big fields is something great that MegaCam can do with its very wide field. Another kind of science we can do is actually imaging individual galaxies. So not a whole group, but actually individual objects. So this is an image of Andromeda galaxy, which is our nearest big neighbor. So our galaxy is the Milky Way spiral galaxy. Andromeda is another spiral galaxy, a little bit more massive, but almost similar mass like Milky Way. And this is an image of Andromeda, and this is taken in optical light. Again, the visible part of the spectrum, and how you can tell that is the disk of this galaxy, which is kind of appears tilted. The disk has a lot of dark lines, dark filamentary kind of structure, and all of that is dust, and you cannot see that dust in optical, so you can make out that this image is actually taken in optical light. The supermassive black hole at the center is right over here, where you can see the big bright blob. So the supermassive center is housed right inside, which obviously we don't see, but we see a lot of light which comes out of that region just because of the gravitational interaction with the supermassive black hole. But this is again a very nice that we can do with MegaCam is we can get the full galaxy in the field of view to do a lot of science, not only in the disk but also in different regions of the galaxy. The other kinds of objects we look at are clusters of stars. So these are this is a very famous Pleiades cluster. We also call it Seven Sisters. So these are all very young, massive stars. And if you remember from the Stephan's quintet image that I showed you earlier, it had those big, bright blue blobs. And these are the same kind of stars that are very young stars that keep forming in this region. All the hue, again, that you see, all the fuzzy structure is all the gas, mostly hydrogen gas, that is glown by the light that is coming from all of these bright stars. Again, something like this is very nicely pictured by MegaCam, and a lot that you can study, not only in the individual stars, but a lot of the structure that's around the stars. Okay. So this is another cluster of stars, but if you can make out, it's not the same as the previous one. So the previous one was an open cluster, where you're not able to very nicely define the structure. Here you're very nicely able to define the structure. It's called a globular cluster, just because it appears like a blob. But basically, this is a concentration of stars at the center of the cluster, and then as we move to outer parts, the density of the stars is scarce. And a very important difference as against the previous image. The previous image was very blue, very bright. This looks more yellow, more reddish in color, and that's because these stars are very old. So these are not the ones that are actively forming. These are ones that have been there for billions of years. So they are quite old stars, which gives them their very peculiar yellow color. And I would like to emphasize that these colors are true colors on the stars. So that really signify their age. The other kinds of science that MegaCam does a lot is actually moving objects. So all of the stuff that we saw till now, the stars, the galaxies, these are all that keep moving in the night sky. Keep moving in the night sky, but at a very slow rate. So they are kind of like, they have very static frames. When you're trying to look at them, we only have to track them as the Earth rotates. But there are certain objects which are moving objects that keep moving, every second, every minute. And these are either asteroids, or these could be comets. And these are other observations that MegaCam is really popular for. So this is a GIF of a 2024 YR4. It's the near Earth asteroid that was not a long time ago. It was predicted to possibly hit the Earth in 2032. But thankfully, there were observations from 6 different telescopes all over the world, and CFHT was one of them. We took observations of this asteroid while it was bright in the night sky, and we were able to track its motion, its orbit, and therefore its motion around the Earth. And we could bring down the possibility of the 3% chance of it hitting the Earth in 2032 down to a negligible value. So this is no longer an issue, no longer a threat to Earth. So it's not going to hit us in 2032, which is good news. So CFHT MegaCam was one of the instruments that was used for these observations. So with that, I've covered a lot about what kind of science we do. At this point, I would like to switch gears to what's happening here. But before that, does anyone have any questions? And I would like to also ask, if anyone wants me to translate any of this in Hindi, please let me know. I would be more than happy to do that. So if anything is unclear, or at any point you want something for me to be spoken in Hindi, please let Nagaraj know, and I can do that. And you can ask your questions in both Hindi and English. There is no restriction. So
Yeah, so at this point in time, anybody have any doubts? Like ma'am was explaining the different types that they use and the different images, and how the place that they have chosen is Yeah, you have a question? Please come to the front and you can tell your name, you can introduce yourself and you can ask them. Yeah, speak.
Hello, ma'am.
Hello?
I'm Shivajit. I'm from Bangalore. I have a question about this calculation about the asteroid. How did you calculate that? How did they predict that the distance and the speed of that, and how can you come to the conclusion that it hits or doesn't hit? How do they calculate the determine the year that it comes?
Okay, so I did not catch your name actually. Can you repeat your name, please?
Shivajit.
Shivajit?
Yes.
Okay. Yeah, so that's a great question. We know, this asteroid is an identified object. So we know the distance to the asteroid and its position, and that's how we are able to locate the object in the sky to take the images. So when we know where the object is, what object we're looking at, we precisely point the telescope to the object. What you see in the image over here, these are different frames. So we have observations taken in different exposures. So these are basically just different exposures. And you see the object moving because it's a moving object, so it's going to move in different exposures. When we see the motion of the object in different exposures, we are able to the different frames. So the position of the object relative to the background gives you its location. And there are observations from other telescopes that are also used in parallel to CFHT observations to actually track its orbit. So these are not only observations with CFHT, but there is another telescope that we also use to collect the data. So the PI of the program, they use data from multiple telescopes, and the data separated in time gives us an idea about where the object is separated in time, which allows you to track their orbit around the Earth. So that's pretty much how it goes in terms of what we observe to do the calculations. The specific calculations is a little bit too much into detail than what's required over here, but the observations itself, the observations themselves are basically separated in time to get an idea of the orbit, if that makes sense.
Thank you, ma'am. Any other questions? Yeah.
Good morning, ma'am.
Morning.
Good evening. Good evening.
It's okay. You can say whatever time it is at your place. So if it's, I think it's maybe afternoon-ish.
Yeah, it is afternoon.
Yeah.
Yeah. Introduce yourself.
Ma'am, my name is Tanish from Bangalore. Actually, I wanted to build my career in astronomy. So I wanted to ask that how can I proceed for further education after 12th?
Oh, that's a wonderful question. So I also wanted to pursue astronomy when I was a kid. So that has always been my dream. So you said you're in grade 12, or are you going to go to grade 12?
Ma'am.
Are you in grade 12? Like,
No,
are you
I
in your
completed my
senior? Are you in senior year of college?
He has just completed his grade 11. He'll be starting his grade 12 classes in a month.
Okay, so I think so the important subjects for astronomy are physics and math. That's kind of where the fundamentals and all the basics come from. So I imagine if you're interested in astronomy, physics and math is something you have always held on to, because that's very important. If you're pursuing a bachelor's, then you want to make sure you take physics and math. There may be programs, so I'm not very familiar with if there are specific astronomy programs in India. I do know there are universities that offer experiments and observations in astronomy, and probably a master's and stuff in astronomy. But physics and math are your basics, and when you start doing your master's, or if you're thinking about doing master's abroad, then you will be able to do it specifically in astronomy. To proceed further, but physics and math are basic. And yes, of course, computer science. That is something that you don't want to leave out, because if you are looking to pursue your career as a researcher in astronomy, that was the one subject that was very helpful for me. So just to take you back in time, I completed my junior and senior year colleges in India. And I did my first year bachelor's in India, but I did not complete my bachelor's. But my first year bachelor's, I wanted to take electronics as a vocational subject, but I could not take electronics because college did not offer electronics. So because I wanted to stay in vocational, I had to go to computer science, which I didn't want it to do. But it turned out to be the best thing that that happened to me during my last year in India. So computer science is at most important. It was very helpful for me when I got to Canada, because you use a lot of programming to do all the research in astronomy. So computer science is another subject you want to always stick to.
Thank you, ma'am.
No problem.
Ma'am, can we move forward? Can we move further?
Sure, yes. All right. So I think at this point we will just check in with Jessica, what's happening in the control room. And
Okay.
did we lose them?
Yeah, just we did.
Okay.
We lost them.
And we lost Jasmine. Oh, Jasmine is
Jasmine's
here.
Jasmine's here.
They're
And
back.
you're back. All right, yay.
Okay.
Okay, welcome back.
Okay, so let us move forward. Let's just check in with Jessica. What's happening?
So right now, the night's going really smoothly. I just finished all our calibration images.
Okay.
I finished our first non-sidereal guiding object, which is what you were saying,
Yeah.
the comets that are coming through. I'm observing those and I'm writing down like pixel coordinates. Finished that, so things should be very smooth for the rest of the night. I don't want to jinx anything, but the weather and the seeing and the extinction, everything is very clear and pretty. And it's perfect right now. I'm gonna say that with a grain of salt because I don't want anything else to go bad.
Okay, that sounds good. So just to back up a little bit about what Jessica is talking. So Jessica mentioned that we already we already started doing science, but we have completed with our calibration images. And we can talk about calibration images if you want to know more about it. But we're just she was pointing out the conditions for the night, and I'll share my screen just to show.
Oh no,
Oh, we lost them
they're
again.
gone again.
Okay.
Yeah. Hopefully they'll be right back.
Okay.
Oh wow, that is a beautiful night.
Yes, it is. It's lovely. It feels so good to sit in the control room when the night is so good.
Right.
Yeah, this is lovely.
Good.
I'm so sorry we had some technical glitch.
That's all right. Okay, so let me just talk a little bit about what I'm sharing right now on screen. So this is so this is actually showing the different weather controls that we have in the control room. And it is basically telling us what is it that we are looking at what places. So let me just take you to one of the image and let's see. Okay, so this is kind of like a movie of how the sky is moving during the night. But if the thing to pick on in the image is you can very nicely see all the stars. So it's a very clear night. We call this a photometric night, which means that the conditions are exquisite for observing. And we have our fingers crossed just so that it stays this way for the entire night, and we are able to do observations all the way till the morning. So this is, it's a very clear night. There's another picture. I think I can go back. So there's another picture showing how the sky is moving. All the light that you see here, Jasmine, is this coming from Hilo? I think this is coming from Hilo.
Yes, that's east facing, so it's looking towards
Okay.
Hilo.
Okay, so this is the east facing camera. So this is looking at Hilo to the east. So there's a lot of light over there and you can very nicely see it. But we are at elevation, not so much affected by the light. So we can very nicely see all the stars and different objects in the sky. So that is where the weather monitoring comes from. All the clouds are visible over here, which are pretty much down and settled. So the part of what the remote observer does is monitoring how the clouds come in, and how the weather is changing, and that is something that they need to do for the entire night. Let me just go back. This is another beautiful webcam pointing up at the sky. And you can see as the night progresses, the sun sets down, we can very nicely see that it's a clear sky. And the band of light that you see passing right in the middle of the circle, that's the Milky Way galaxy. So much clearer than what we can see from the sea level. Okay. Oh, this is another one from the Subaru All Sky Cam. This actually shows the different colors too, so you can actually see the Milky Way much clearer here than in the previous image. So that's again a webcam pointing up at the sky. And this is our channel, which has all the different webcams which belong to different observatories. They're basically all they all function together. Okay, we lost them again.
Mm-hmm.
Okay.
And they're back.
Oh, they're back? Oh, they are. Okay. So all of these webcams, they operate all together, and together they can give us a complete idea of how conditions are changing up at the summit. I think with that, that is also helpful because not a lot of, I think just 2 of the observatories actually have staff up at the summit doing the observing. Rest of all the observatories do remote observing. So I think with that, what I'll do is I'll pass it over to Jasmine, and maybe she can give us a quick walkthrough about what she does as a remote observer, because we're not physically at the location of the telescope. We are over here in the control room at the sea level. So Jasmine, maybe you can give us a quick walkthrough. And if you want me to point out to different stuff as you're talking, just let me know and I can do that.
Okay, perfect. Maybe I'll share my screen. Let's see if I can do that.
Sure.
No.
Yeah, that sounds
Perfect.
good.
Yes, you should be able to share your screen now.
Perfect. So I'll go to the same website that Raja was on. So we start out looking at this forecast tab. This is produced by the University of Hawaii. They have a service that does particular forecasts just for Maunakea. So we'll look at this. This top line would show the percent chance of fog. The next one shows the percent and height of cloud coverage. So we see there's no chance of fog or precipitation through this week. No clear skies, and then the next ones show temperature, how much precipitable water is in the atmosphere, and what seeing is like. So it looks like seeing will be very good for the rest of the night and actually get better. So this is kind of what we'll first look at to decide if we open right away or if anything looks a little bit unstable, we might question it a little bit longer. So going to a similar page to what Vidyadhan showed, other observatories have their cloud cameras up as well. So this doesn't want to load nicely. We'll go to instead. So we'll just look at like particularly the east facing one. And this is where a lot of the fog would come from in this direction where we looked towards Hilo. So we look if this inversion layer looks stable. If it's a little bit higher up, like here, we might expect that some fog is going to come through. So we watch that very closely when we're deciding whether we observe when we're starting the night. Also, if we think that the forecast shows that it has a higher chance of fog, we will watch this area very closely. It also maybe, depending on the direction of the winds and looking at the satellite, we can know maybe where some of the bad weather is going to come from. So we'll look at satellite page. You can see there's not a lot of stuff around the islands bothering us. So why it looks clear, there's a bit of stuff now to the north here, but that could break off later. But it looks like it's nice and clear around us. So we'll look at that too through the night. Like if we're expecting fog might come later, we can also satellite is approaching. And like Vita just said, there's only usually 3 observatories, sometimes 4 at the summit. The Keck Observatory, Subaru, the NASA IRTF, and sometimes observers from SMA go up. So when that happens, they are usually very good. We communicate on Slack about whether the road is getting icy, if they see snow falling. But we also, because of the remote observing and transitioning to it, set up a lot of these cameras. We have sensors as well that will tell us whether there's precipitation, if it's rain or snow. We can see if humidity starts to rise. We might know fog is coming. So we watch all of those things very closely through the night. And on nights like tonight, when we don't have to worry about the weather, it's best. So that's usually how we start the night, with those kinds of things, and what we monitor through the night with regards to weather.
Sounds great. I think there is maybe one more thing. So I can share my screen and we can point at that. I was hoping that you could cover. So there is this screen where we are looking at the size of the particles. So can you talk a little bit about what we are showing over here?
Yes, so that shows the particular count of between the size of particles in the air. So right now it's nice and flat, but when you have volcanic activity, as we do, we want to make sure that we don't have a lot of particulates in the air. We expect the dust might be like sulfur dioxide or other things that could be from a volcano. So if it goes above certain thresholds, depending on the humidity, then we want to make sure that we aren't observing, because if it's humid and there's sulfur dioxide in the air, it will interact and become sulfuric acid, which is not good for the mirror coating. So that's something that we had to look at very closely when Mauna Loa was erupting particularly, but usually with Kilauea, it hasn't been so bad this run, but we we just watch that depending on the directions of the wind to make sure that there aren't volcanic particles in the air. But we also recently did get a SO2 monitor as well, so that'll help us a little bit more.
Okay, so does anyone have any questions on that part?
Any questions? Any questions on the weather, on how to prepare, anything like that? No questions?
Okay, so I think then we will move on, and I think at this point what I'll do is I'll actually give you a quick 360-degree view of the room. So I'll move my laptop and I'll show you around with my camera. So where should we start? Maybe we can start. All right. Can you hear me, Jamika?
Yes.
Okay, all right. So I'll actually start at the door entrance because that's where I usually start. So that's the door that you see there, that's the entrance to this control room. And there are two entrances, one on this side and one on the other side. So that's one of the other doors. You can then see an image of like a big image, which looks kind of lit up. It's actually our infrared, near infrared spectropolarimeter. Do you see that? Okay, so that's an image of one of our spectropolarimeters. On the top, just beside the exit sign, you can see a monitor screen. And that is basically showing the status of all the different things that are needed to for the operations to go very smoothly. So if any of all the buttons, if you can see over here right now, are green, and the green means that everything is functioning very nicely. If there are any red ones over there, then the RO needs to immediately report those things to the concerned people so that they can take care of that and operations can proceed smoothly throughout the night. Then over here, we just have a couch and a lot of stuff for our remote observers. We have a fridge where they store their stuff to eat. This is the screen where we can see all of you right now. So that's our monitor screen in the control room. These are our weather screens. Most of them are weather screens. The one that you see right over here, it's that's our the telescope control software screen, and I'll talk about that a little bit later. But that's one of the things that's very useful for the remote observer. The remote observer sits over here, so that's where you see Jessica right now. She has a bunch of different monitor screens in front of her, and she keeps a watch and operates all of them at once, all the time throughout the night, and that's for 12 hours straight. So quite a big job that Jessica has to do, but it's simpler on nights like today, where everything is clear and you don't have to worry a lot about messy things with weather. So that's kind of how our control room is. And I'll turn off my video now. And I'll share my screen to show you a bunch of images of the actual telescope. Okay, so can you see my screen?
Yes.
With okay. Let me just do this. Do you see the image of our headquarters? Okay, all right. Just making sure I'm sharing the right screen. Okay, so this is our office, which is in Waimea. So that's the front entrance that you see there. And that's the picture of the control room that I showed you around just now. And if we compare it to a different control room, so this is our control room, which is up at the summit at the observatory. So that looks very similar to what we have in the control room. You can see there are a lot of different controls all around the weather screens up at the summit. And that is just a bunch of different things that need to be monitored when you are up at the summit. But it's pretty much similar to what we have over here. So when we are up over there, that's basically the desk where all of us are seated, and we're working on different things with respect to the telescope. So that's that. This is a picture of the room where we have our computers and where we all have all the controls where we relay the data up and down. So that's a picture of that. And then this is our telescope. So this telescope has a horseshoe mount. And what you are looking at over there is this is an instrument which is mounted on the telescope. This is the upper ring of the telescope, and the bottom ring of the telescope I'll point it out a little bit later, but this is the bottom ring of the telescope where you can actually see the primary mirror. So this is the primary mirror, which is the 3.6 meter diameter mirror that I mentioned to you earlier. This is the upper enclosure that you saw in the previous image. That is this white enclosure over here. And that is the house of the secondary mirror, which is on the top. So if we look at the previous image, this is the primary mirror at the bottom. And all the way up over here, where you can see this white ring, that's where we have the secondary. So that's our secondary mirror. This is another view of the telescope. So you can see the entire telescope vertically. Down over here, the white part that you see, that's where the primary mirror is again. And all the way up over here, we had the secondary mirror, but right now the secondary is swapped for the MegaCam instrument. So the instrument that you see, this is MegaCam. And that is the one that we are using right now. So whenever we have to observe with our imagers, we basically take out the secondary mirror and we mount the imaging instrument at the place of the secondary mirror. And we can talk a little bit more about that if you have questions, but that's how we do it for our imaging instruments. For our spectrographs, so we have 3 spectrographs, as I mentioned earlier. For the spectrographs, we have to mount them at the bottom of the primary mirror. So that is right over here at the bottom of the primary mirror. So you can see that in the image. So this is the bottom part of the primary mirror, and that is where all our spectrographs go. So when we observe, the light comes all the way down, and it and the detectors of the spectrographs, they basically detect the light. So this is a close-up view of all the instruments which are right at the bottom, all the spectrographs. Again, the primary mirror is inside this white, big, thick white enclosure. You cannot see the primary mirror like that. All of the boxes that you see over here, these are slots for counterweights. So you need to put in counterweights on the telescope to balance the weight of the telescope as you take up and down the different instruments. So that's where the counterweights go in order to balance the weight of the telescope. This is the MegaCam instrument, the one that looks like a disco light instrument. It's a very cool instrument to just look at, but that is what is right at the top of where the secondary mirror is right now. And to show how the inside of the instrument looks, so this is actually the full detector view of the MegaCam instrument. So inside the instrument, we have this detector. This is the whole thing. It's made up of 40 different CCDs. And every CCD works with 2 amplifiers. So every rectangle that you see over here, that is one CCD. So this is a mosaic of 40 CCDs, each functioning with 2 amplifiers. Just to show you a size scale, a very small coin is right over here. So this is a size scale, just to give you a sense of how big the CCD is. So this entire CCD mosaic, when it's looking at the sky, it's looking at 1 square degree patch of sky. So that's 1 square degree by 1 square degree square part of the sky that the instrument is able to capture at any given time. And just 1 square degree by 1 square degree may not seem a lot, but it is actually quite big in terms of how much you can picture at once of the sky. So I think that's pretty much it with regards to the to how the telescope is. And just to give you another view, I think I have this is another view of the I'll give you a view of the primary mirror. I took a snapshot of this while Jessica was opening up tonight. So this is how we can actually see the inside of the dome. So just to give you context, there are cameras all inside the observatory, literally every single place, because we want to monitor what's happening inside the entire observatory while we are down over here, just to make sure everything is working fine. So there are telescopes, there are cameras inside the dome to monitor every single movement that's happening inside the dome. And when we are opening up for the night, we do everything from the control room over here. We don't do anything from the summit. So when we have to start for the night, as Jasmine said, they check all the weather and stuff, and then the remote observer does all the opening part. So maybe Jessica, you want to talk about what all stuff you do after the weather check, just in terms of opening up the observatory? And maybe you can point out stuff.
I'm trying to think of like a better way to show this because everything's so dark inside
Yes.
the telescope
And,
right now.
and you cannot see anything inside right now because all the lights are off.
Are you
because
able to
we're
show
on-
sensor or is that too?
Yeah, no, I'm able to show that sensor.
So other
I'll
things
stop
that
there.
we take into account when opening up is things like the internal temperature of like the humidifier room, looking at the computer room temperature, making sure that everything is within our limits for opening up. I think I'm more concerned about like looking out for clouds while things are opening up, and such as like the shutter and the mirror cover, because that's the most vital for observing. But we also look at the machinery room, looking for any like oil spills, anything that could cause trouble during the night. If we go to StatServe, wondering like things like that, that's our machine room. Hydraulics room, we look at the ground for any like oil spills, we look for any wires that might be out of place. Because although we can't control that from here in the control room, we can report that. And if it leads to something like a bigger issue, we can tell someone to go up and like take care of it, which has happened in prior nights. We've checked out like the computer room temperature or checked out the hydraulics temperature. And sometimes things are outside of our limits and we need to send someone up. Sometimes us ROs, we go up to like help out. And yeah, very important. Something you don't really think about during the night, but it's something else that we're keeping track of as we're sending out exposures and keeping track of weather, all of that combined.
Yeah, and this is also something that the RO needs to take care of throughout the night, because it may happen that even though conditions were very smooth and okay inside the dome and inside all of these, wherever all of these systems are throughout the observatory, there are 5 different floors to the observatory, including the basement. So the RO has to monitor all of this stuff all throughout the night to see if the temperature is not rising, if everything is functioning fine, if all there are no issue with like leaks anywhere. Because if there is an issue, it needs to be taken care of immediately. So then those are the times that Jessica was mentioning. We need to have designated staff members go up to the observatory, even though it's night and like 12 a.m., but they still need to go up there, make sure that everything is fixed, and we can resume our observing. Because we don't want to break the science observing part at any point. The science output that comes from the telescope is the most important part, and we always want to make sure that we are able to do maximum possible science during a given night. So that's our top priority when we're looking at the priority of things. Yes, and then I was showing earlier, I'll stop sharing this. Yeah, so this is where you can actually see the telescope mirror, the 3.6 meter mirror I'm talking about for the whole time. The cones that you see, which are to the walls right now, these are the cover, that's the mirror cover. It has a very beautiful casing that falls on the mirror, but that is basically the mirror cover. And right now, when Jessica opened up tonight, those mirror covers came off, and that's how the mirror is exposed to the night sky when we are pointing the telescope in different directions. So, and this is an image of the dome shutter as it was opening, or I think it's fully opened at this point. When I was seeing it, I think you had already opened the dome shutter. I can't make it quite from the image.
You can tell if it's open based on this one, I think. I think it's almost
Okay,
open.
yeah.
A lot.
Yeah, so that's the what you see over here, that's the dome shutter. And we open the dome shutter when when we are starting up for the night, and then when we are done in the morning, we basically bring down the shutter, close the mirror covers and everything. But the dome shutter is basically when we have to point to different parts of the sky, we move the dome shutter accordingly. And there's a mechanism where we can how should I say that, when we actually couple the motion of the dome along with the telescope so that it's in the tracking position. So as the telescope has to point out to certain object, the dome will automatically move to that part. So it will expose that part where the telescope can point to the object and do observations. So I think that's a lot of information. So I'd like to ask if anyone has any questions at this point.
I think it is so much fascinating to see all these things. Yeah, because we have just heard about these things and probably never gotten exposed to such detail. So, yeah, so any questions at this point, students? No, no questions?
Yeah, that's absolutely fine. And I totally understand, because I am coming I'm coming from a place where you were I'm coming from a place that I can see you all right now. So I can totally imagine what you must be feeling. When I was in my grade 11, so that's junior college in India, I I did not know anything. So I did not have a lot of, I had some knowledge about astronomy because I used to read books on astronomy, but I never had seen a live telescope. I should admit that. The first time I ever saw a telescope was after I came to Canada. I was at the University of Toronto in Toronto, and that was the first time I participated in outreach. So I was in my third year, and that was the first time I got trained on how to observe through a telescope. And Jupiter was the first object that I looked at. So, so it was like 4 or 5 years after my junior college that I actually looked at a telescope and looked through the telescope. So I totally understand.
But again, Shadow the Scientist has enabled this, and it is helping us to kindle that curiosity into space, right? That is amazing. So yeah.
Yes, yes, I think that's really appreciative, and thank you, Jamika, for having us all together. I think it's a very incredible initiative to take science, not only astronomy, but in different disciplines, to students and in general people who do not readily have access to all of these kinds of things. So thank you so much. And yes, at any point you have any questions, even if it is something silly that you think it is silly, please feel free to ask. Please do not hesitate. I would love to answer questions. So please do so. Okay, I think what we can do is we can take a look at some of the data that comes in. I'll show you some raw images. So we did look at some of the very beautiful images with MegaCam, but that's not how the data comes in. So I'll just share my screen again. So sorry, okay, so actually before that, we'll take a look at how the data actually comes in through the telescope. And I'll play a quick video for that, but just give me a minute to get it started. Can you see the video? Okay, so let it play, and then I'll talk about what it's showing. Okay, so we'll go all the way back, and I'll describe what's happening in the video. So this is basically showing how observations how the light is collected by the telescope and how it gets transmitted to the remote control room in Waimea. So this is basically, we're looking at some object in the universe. The light from the object travels all the way down to Earth. And on the Earth, we are in Hawaii, collecting light at the Canada-France-Hawaii telescope. This is the surface that you see over here. That's basically showing us the primary mirror. So the light falls on the mirror. So the entire diameter of the mirror collects all the light. It gets reflected up to the secondary. Or in this case, you can see this is a long instrument. So this is actually our imager. So the imager directly picks up the light. So the light gets reflected to the imaging instrument, where the light is recorded with those CCDs. So the image gets recorded on the detector. And once the image gets recorded on the detector, from the detector, so that's what it's showing. As the telescope is moving, it keeps recording the light. And all the light that gets recorded with the detector, that is transmitted through internet all the way down to Waimea, to our remote control room over here. So we can see all the data on our monitor screens as it appears, and we're able to look at all the observations. So that's basically how the telescope works. And when we are looking at the data, so looking at a raw image is not the same as looking at a final image. So we saw MegaCam does produce beautiful images, but this is how the raw image looks like. So you can see this image it's basically every CCD records a certain part of the sky. So this is the entire image that was recorded by the full CCD of MegaCam. And this is looking at a very faint object, which you can see right over here. It's a very faint galaxy. I can zoom in, right? So it's a very faint galaxy. It's a spiral galaxy because you can see the arms of the galaxy, but this is a very, very faint galaxy. So in the field of view, what you can see, the dark spots. The dark spots are all the areas where light was recorded. So these are all either stars or galaxies in the image. And the rest of the brighter part is all the background. That is where there is not a lot of light coming from. So this can be one other thing which could be confusing depending upon how you adjust the coloration of your CCD image. You can either view the light in black or white, and the background will be accordingly. So in this image, all the dark spots are wherever light was recorded. So these are either stars or galaxies or whatever. And all the whiter part is the background part. So that's an example. This is another example, and you can very nicely see the galaxy in this case, because it's probably a very bright galaxy. So it has a very a strong contrast on the image. Usually when we look at objects, we center the objects in the CCD detector. So that is ideally what we want, because the central part of the detector is the part that is most farther away from all the problematic areas. So the edges of the detector could be a little bit problematic, but the central part is far away from all of that. So usually we want to center something, center on something, and then that appears right at the center of our detector image. So this is the galaxy that was being studied in this image. So this is another picture where you can see the galaxy right at the center. This is another example. I have no clue what was happening over here. It was probably light from some object or some kind of artifact, but I have no idea. It kind of looks like a real thing that has happened. It does not look like an instrument artifact thing. But again, when you are imaging, there are certain things that you need to be careful about in your data. So these are the kind of things you have to be mindful of. One other thing I would like to point out is if I zoom in on this, you can see that there is some kind of a ring-like structure, a thick ring-like structure. I don't know if it's very clearly visible, but there is a ring-like, very faint ring-like structure, and that you can make out immediately is an artifact of the detector. It's not a thing in the real image, not something that is up there in space and you have captured that. It is very much off of the instrument. So these are things like that, they have to be corrected when you're processing the images. And I'll talk a little bit about that later. But when you're processing the images, we want to make sure that we clean our images for all of these different structures so that they do not appear in our processed image. Otherwise, the analysis will mess up with the analysis part. You can actually see it very clearly in this image, however. So this is a very, very bright star. And you can very clearly see the ring around the star, which is not at all real. It's because of the instrument. This is something that they call like a, I believe it's called like a positive, I'm trying to remember the name. I can't remember the name on top of my head, but it's basically an artifact of the instrument. And when we are processing the images, we make sure we subtract such artifacts from the image. This is also something else that we need to take care of. And this is when the light from very bright objects leaks into the surrounding pixels. Then we can have artifacts like this. So maybe Jessica or Jasmine, do you want to like maybe say a few words on what you would normally do if you have something like this in the image?
In the image?
Yeah.
Like grading wise, or like
General, yeah. What do you do?
So when I see something abnormal in the image, I think the first thing I try to do is either check online, because there's that whole MegaCam database that Heather, our colleague, has, where she reports every anomaly that we see like throughout the years. If it's something major, I would comment on it, because throughout the night we're also commenting on every exposure and every picture that we're taking. So I report it, and maybe if it's something like major, I'd grade it like a 3 or a 2, which is adverse to like a grade 1, which is a perfect like casual usual image.
Yes, so something like that is specifically noted down by the remote observer if it is not typical to observe in an image. But this is what this kind of thing is usually observed when we are looking at very bright objects, and you can have leaks. So you have to be, so that's one thing that when the scientists who request data are planning for their observations, they have to make sure that the object that they're observing does not become too bright with their exposure times. So every image has a set exposure time. Maybe you observe that image, that object for 60 seconds. Maybe you are exposing it for 100 seconds, or maybe like 1800 seconds. Exposure times are typically measured in seconds. So if your object is bright and you have a long exposure time, that can saturate the pixels that collect the data for your object, and you do not want that to happen, because if you're saturating, then all of the saturated pixels of a given image are flagged as bad pixels. And when you are trying to process the data, all of the flagged pixels are not taken into account to construct the full image. And so so you have to be very careful when you are planning for observations for bright targets, for example. So as we are slowly getting into talking a lot about the processing of images, so these are the raw images, but for going from raw images all the way to a processed image is a very, very extensive process. So there are like there are many different steps that you have to complete properly in order to go from a raw to a final image. So we start with the raw image taken with a telescope, but there, as you saw, there are lots of different artifacts in the image. Some of it comes from the cosmic ray hits. So these are random charged particles that keep moving in the universe, and they keep hitting your detector. They get recorded. And you do not want those kinds of cosmic rays. There's another issue that you can have. As you can see, there could be pixel leaks. The detector is not a perfect equipment. It has its own response, its own behavior, and because the detector has its own behavior, the all throughout the detector, all the different 40 CCDs do not get equally illuminated, or I should say, they do not equally respond to light the same way. So what we want to correct for is the response of the detector. So that's another thing. There's also when you picture like bright objects, there is some amount of saturation, some amount of light that remains back in the detector as it's being read out, as the data is being read out, and you want to correct for that. So we do take dark images, and what it means by dark images is we basically take images with the detector pointing at a very dark surface. So it's not pointing at anything which is lit up, but we are basically collecting images in the dark to see how much saturation do we get in the pixels. And that's something which is important. So when we are trying at the first stage, when we are processing the image, we basically have to clean up the image for all of these different artifacts. That's the first stage. So once we clean up all the image, we have a good image where we do not see any artificial features on the image. At that point, we want to stitch the image together. So you can see right now all of the rectangles, the detector patches, they appear separate. We want to tile them up all together, so that we are able to see one complete image from the instrument. And after that, we basically make sure that all the coordinate positions of all the objects are correct. We make sure that we have a reasonable light from all the different points in the pixels. So that's the later stage, and then finally we have the full constructed image from MegaCam. And just to show the first part where I talked about the detector response not being equal. So the detector can respond, the different parts of the detector can respond in different ways. And to understand how the detector responds to light when it's illuminated, we actually do flat fields, so flat images of the sky. And that is something that Jessica did when she first opened up and actually started taking images. So these are the kind of calibration images, but those that are used to calibrate the response of the detector through its entire field of view. So that's what flats are used for. And I'll show you an example of flat. So this is a flat image, and it may not quite look as a flat as in equal coloration on all parts of the detector. But a flat, it does not mean that we will see we will see every single rectangle in the same color with the same pattern. But it is basically showing us how each of the detectors is responding to light when it's illuminated. And that is the response that we model, and that model is subtracted from the data so that our data is free of that unequal illumination, the specifics of the detector response, so that we are then able to measure how much light is coming from every single object without any bias to different regions of the detector. So that is when a flat field is used. And these are flats. What you're looking at in the flat image is basically a plain sky. So when the remote observer comes in, and let me see if I can point out what I mean by a flat. Okay, maybe it's useful to look at this image. So when we want to take flats, we usually take those in the evening time, so before we are starting the actual science observations. And we also do them in the morning time when we are done with all the science. But again, we are able to look at the plain sky. So when we're doing flats, it's not yet sunset, so the sun is still up, but you are able to see a clear patch of the sky. So we want to still have, so that's still a photometric sky, meaning that we are still able to see clearly in the sky. We're not looking at clouds. There are no thin cirrus clouds, or there are no cumulus thick clouds. We're just looking at a plain patch of the sky, and we are imaging that plain patch of the sky, because what that means is light is coming almost equally from the entire patch of the sky that we are imaging. So we have equal amount of light falling on the detector, which allows us to carve the response more nicely. So we want to have a photometric sky, not yet sunset, but still a plain patch of the sky in order to pick up those flats. So what you see in the image over here is basically that sky, where we do not yet have any, where we cannot yet see any objects, but this is just plain sky. So that is what the flats are. And if you look at the image a little closely, you can see sections over here where you can make out those spots. And these are the things. This is something from the instrument. It's not real from the sky. So these are all the things. So flats also need to be processed to clear up the bad pixels of the image and stuff. So so flats also go through the processing part just to clean up the bad pixels and everything, and then they are used to correct the science images as well. So this is kind of an extensive process. I know it's kind of a little long, but yeah, any questions, Nagaraj?
Yeah, any questions, scholars, at this point in time? Yeah, please. Ma'am, and also a small heads up, because today is the last day. Few of them have to start traveling back, so their parents have already arrived, apparently. So
Yeah.
yeah.
Ma'am, myself,
You
Prajwal.
can come little back. Yeah. Speak.
Myself, Prajwal. Ma'am, I have a doubt. Is there any real image of complete Milky Way galaxy, and how was it taken?
So so is there a real image of the complete Milky Way galaxy?
Yes, ma'am. And how was
Uh,
it taken?
So we do not, so this is a very good question. We do not have an image of the Milky Way galaxy, a complete image of the Milky Way galaxy, because we are sitting inside the galaxy. And this is the question of perspective. When you are inside something, you cannot image that object from outside. Just as you're sitting inside the room right now, so you cannot take an image of the entire building. It's similar to that. So we are in the galaxy, although we're not, we are quite at the edge of the galaxy, but still not outside the galaxy to take a complete image. So all that we know about the Milky Way is from the observations of different things that we have looked around us. So the different stars that you see, the solar systems that you see, the way we see the Milky Way band, that's basically the disk of the galaxy, because when we are sitting at the edge, we can only see the galaxy in the form of a band. We cannot have an upward or downward view of the galaxy, but we can have a side view. And because we are having a side view, instead of appearing like a round disk, it appears like a plane a plain line in the sky. So there is no real image. Everything that we know is from observations of different objects, and by studying objects which are similar to Milky Way, such as Andromeda. So Andromeda is, again, another spiral galaxy. And by comparing observations to observations of different galaxies, we're able to study a lot about how Milky Way might be. So we are able to construct an artist conception of how Milky Way would look like, although we cannot image it from outside. Does it answer your question?
Yeah, ma'am. Ma'am, and I have another question, another doubt.
Sure,
When you showed
yes.
the first image of different galaxies, could we find any black holes in there?
Oh, that's a very good question. And so so black holes are tricky in the sense black holes are black, meaning they do not emit light. So you cannot directly image them. However, we did have recent observations, direct image observations of not the actual black holes, but all of the light that comes from around the black holes, which is as close as you can get to imaging a black hole, at least technologically right now. What you see in the image does not actually show you black holes, but all the massive systems that you see, such as this galaxy over here, there are galaxies. So this is another galaxy, this is another galaxy, this is another galaxy. So all the galaxies that you see in the image over here, all of them host supermassive black holes. And there is a distinction there because black holes are of different masses. You can have stellar mass black holes, which are about 20 to 30 times more massive than the sun. So they are basically tens of solar masses. Or you can have supermassive black holes, which are millions or billions of solar masses. So millions or billion times more massive than our sun. And all the massive galaxies that you see over here, these host supermassive black holes. So although we're not able to see the black hole directly, if I only zoom in on this galaxy, right at the center, the brightest blob that you see at the center, that is where the supermassive black hole lives. So although you're not looking at the supermassive black hole, you're looking at you're looking at the region inside where it sits. So so you're looking at supermassive black holes indirectly, but not directly in this image.
Questions? So how are you feeling? How was this session? Sorry, ma'am can hear. Be loud. Did you learn something new? Did you see something new? right, ma'am? Right from how the weather conditions monitored, right from how the telescope looks inside, and right from how the raw data comes to them, from that raw data, how they extract, and how the light enters from the object to the telescope, how that is processed, and where the office is located, how it is operated, right? So I'm sure few of you will be interested in astronomy. This session can kindle that interest in you, right? So lot of things are there to explore. So one of the main things about this camp is also to make you aware of different arenas of uh, things that we can learn. And astronomy is one fascinating thing. So from tonight, please go to your terrace, observe the night sky. There is so much happening there, right? Through our naked eye, also you can see some of the miraculous things that is happening out in the sky, right? Ma'am, would you like to add on to that?
No, I think that's a very nice summary of what we did today. I really hope I totally understand it can be overwhelming. This was a lot of information covered in 2 hours, so it's not possible to grasp and absolutely understand every single bit of it. But I would encourage, if you're interested and would like to learn more, you always explore your avenues, reach out to people. I think talking and letting people know that you're interested, what you're interested in, and what you would like to learn is the first step that you can take. So I would really encourage you to seek for opportunities, and keep exploring your curiosity. That's very important. So thank you so much. I hope you were able to learn at least one single thing from the entire session. I would be glad. But yeah, thank you so much for joining.